And what's a happening, YouTube? Wild Ox Studios here, and today we're going to talk a little bit about uh, virtual reality and Godot. Um, so, if you're familiar with my channel, you'll notice that I have a really long-running experience with Unreal Engine 5 or Unreal Engine, not just Unreal Engine 5, but Unreal Engine. Started development in Epic's ecosystem like pretty long time ago. Um, have a little bit of familiarity with UDK, Unreal Engine 3, a lot with Unreal Engine 4, and then, you know, UE5's been out for some time now, so most of my work takes place there. Um, Over in my Discord, and as part of the VRE community and Oculus Start community, I've been actively involved in helping people ship products and games to Meta's ecosystem. The Quest 2, the Quest 3. So I've shown a little bit of my age, but even the Go before the Quest was a thing, I contracted for a couple of companies to get games out there. So um, today we're gonna talk about basically the differences between the two engines. And what I love Unreal Engine 5. It can scale really well. I've said this in like my performance overview. I talk about forward rendering on VR. Like I've spoken on like the optimization pipeline that they followed in Robo Recall, and I've mentioned that's a really good source of reference material to go back and look at. Unfortunately, a lot of things have changed kind of over time. Um, Unreal Engine 4 has a little bit of an easier time targeting Quest than Unreal Engine 5 does. Um, they're moving more towards like virtual light maps, away from traditional light maps. They're pushing that quality bar even higher. So they've deprecated like ES3 support. They don't even support GL anymore. So it's ES3.2 now. They're trying to unify the mobile rendering pipeline. So like Metal and higher end Android devices run Vulkan by default. But I would state like even their Vulkan renderer versus like say Unity or Godot's is a little bit more taxing on hardware. And with the Lumen and Nanite and SM6 changes that are kind of coming, PSO caching, et cetera, et cetera, it seems like that bar is just being raised higher and higher and higher. So I wanted to show you guys a video. So this is a scene. By the way, this is running in compatibility mode, and this runs in a web browser, by the way. Really good light bake information. I mean, the shadow quality, there's a little bit of banding here, but I mean, for what you're getting, for this to run on like a 2011 Kindle Fire at full frames, this little engine that could is really impressive when targeting mobile platforms. Keep in mind that Godot has a mobile renderer and a forward plus renderer, and I would argue that the forward plus renderer is even further along than Unreal Engine's implementation of forward rendering. They're very similar, but Godot just has a like nice feature after nice feature after nice feature. So like in the Unreal Engine talk, and I'm going to show you this thing running natively on the Quest. I'm just going to pull up a video I had recorded. If you're a member of my Discord, you've likely already seen this. I've played it for you guys, but this is me in natively on the Quest 3 in this scene, and it looks gorgeous and runs butter smooth. And I have tested this across natively on the Quest 2 and the Quest 3, so there's absolutely no issues. Another thing I want to mention is I have a community VR template, and I've done 4 videos on that. So if you're interested, join the Discord, and the Git is provided in those in those videos. So feel free to get actively involved and leave some suggestions on what you would like to see in the template. This content, this entire thing here, is part of the Wild Ox Studios community template, and it's public, so you're open to join and collaborate on this, and offer suggestions, or even fork it and ask for PRs to be merged back in. But this is a baked scenario. In previous videos, I have a dynamic shadows scene. So this is what I did was I created this tool here, and this runs natively on the Quest. So it's a full dynamic day-night cycle with moon, stars, casted shadows, everything. And this is in compatibility renderer, running on the Quest 2 and Quest 3. You will need to have foveation enabled on the Quest 2 because it does start bumping into GPU level 4, but it runs fairly well. But if you're looking for something like a stationary scene with like fog, dynamic clouds, and you can afford to bake your lights out, you don't deal with this shadow distance that you have from other engines, because you get to transition between fully dynamic, really close shadows and fully baked, really far shadows. Now, if you've seen a lot of the videos that I've done in the past, I've covered where Unreal Engine also has the capacity, which I think these are all my latest Godot videos. I'm gonna see if I can find the epic video for you guys real quick. So if I pull this up, you'll see that this is a video I recorded, and I have this video up on the YouTube as well from UE5. And one of the things you'll notice is, for one, the shadows are baked out here using a distance field type shadow bake. Two, Unreal Engine handles light maps on a per object basis, and it builds out a list of these light maps, and each one of these light maps are going to have like 64 KB, 256 by 256, 1024 by 1024. So like you're defining that resolution and that scale for each one of these light maps that it bakes. And you still end up with, like, you can see it on the edge here, some mud. And if you've played any Unreal Engine games, you've noticed this when playing those games. The other thing that you'll notice too is that even with the distance field, pre-computed distance field bakes, you end up with some noise that some engines do better at and some engines do worse at filtering out that noise. So you end up with a really harsh line and then basically some softening, and the denoiser, can or maybe will, maybe won't take care of that noise level. The other thing is Unreal Engine uses a Cascade Shadow Map functionality, and you can see some of that noise here. So it uses Cascade Shadow Maps, and the shadow map resolution is cut back heavily on mobile renderers, and you can override this to some degree on Android, but there's only really so much that you're going to be able to push this with the fact that a tile-based GPU like the Quest 3 has to look up, one, it has to render these shadow maps in real time, and then two, it has to look up all of these light maps for each one of these objects that light's been baked on, whenever they're being cold or uncold from the GPU. So those texture lookups are a little bit heavy on a tile-based architecture and memory management. Thus is where like they've tried to go to VLMs, which is virtual light maps. Now, the problem with that is it's more of a memory management architecture. You're still looking up segments of the textures to feed into memory, and they're still individualized, piped out files, and if you've ever looked at storage management, even with the compression offered with different methods on Android, ASTC, I believe, you're still paying a lot for light maps. Like, and that really hurts the VRAM budget if you're looking at when you load one of these games, and also hurts storage capacity. So what is Godot doing that's so much different? Well, Godot is a very, very low-end renderer that targets WebGPU, WebGL, and low-end mobile and 2D games. So it even has a 2D rendering pipeline. But what it does is, when it does its light bake, for once, I guess another thing too is it's probably not emphasized enough, but Unreal does a lot of abstraction for you. Like, it builds this layer of, I'm going to do so much for you to make your life easier. But in that process, it also makes life a little hard. For one, Unreal Engine uses chaos, and trying to use something like Havoc or PhysX, going back to PhysX, which is what UE4 used, by the way, and is far more performant for low-end devices. It's a nightmare trying to switch off of chaos in UE5 to go to something like Havoc, or implement your own physics engine like Jolt. In Godot, the physics engine is a module that is easily swapped in the project settings. You just go to project settings, you find physics. If I can spell, PHYS, and you just enable it. So if you go to the physics 3D, you see this drop down. You basically can swap physics modules in the project settings. The other thing is that in Unreal Engine 4 and 5, if you're running MSAA, you're going to deal with like having to like keep a fine-tooth comb over your roughness values and specular values, because you're going to end up with specular aliasing, because TAA actually overly smears the screen. So all of your asset materials are basically blown out in the specular channel to try to like overcompensate for the lack of good specularity in TAA, because it over smooths. So Godot has actually introduced a method of kind of dealing with this at the project level. And it's this screen space roughness limiter that you can enable if you don't want to go through all of your materials and rework them. It'll basically give you some smoothing or a clamp value on the specular aliasing issues that you would have, because you're in MSAA, you're actually rendering the full roughness and specular value out to your HMD. So there's, that's one thing out of many, and I could keep going on. So what's the other thing that Godot does differently? Well, whenever you're defining your UV coordinates for your light map, they have these things called size hints. So they're kind of like Unreal Engine in the sense of, you're not basically specifying the actual size of the light map that it's going to build. You're specifying the size that you want this portion of the light map for this asset to take up in the final EXR file. And as you can see, the entire light map is just a 2K texture. So it's packed everything from the scene into a single 2K texture, which is only 16 megs. So instead of, hundreds of megs, you're getting all of your shadow calculations put into a single texture, an atlas texture, similar to like old school games where your entire shader, your entire master material, or even material instances may have read from an atlas to color your entire game. And this comes with huge performance benefits on tile-based GPU architecture, because it can store this one atlas in memory and look it up for every object in the scene. It doesn't have to do a new lookup for every single object. The other thing is that Godot technically still supports OpenGL, or that is what the compatibility renderer is. And while the Quest does support Vulkan, and they have moved to Vulkan, especially Quest 3, the Quest 2 is still happier rendering with a lighter GL-based shader model, a very simplified shader model. So that GPU was just built with that in mind, that was the technology at the time. So this renderer, the Godot renderer, just seems to have feature sets and material abilities or methods that it does to make the Quest hardware happy. The other thing is that if you've been in Unreal Engine 5, you'll understand like it is very, very difficult to set up like an environment that has a sky and uses like a panorama at a reasonable size. This is only a 1K texture and baked out, and looking at this on the headset looks amazing. And you have multiple like MIP filter options, no MIPs, linear MIPs, and then you have like re-import options here where you can tell it when it imports how you want to compress this, which again, this is 682 kilobytes, which is extremely small and does very well on the headset. So I'm going to start calling Godot like the little engine that could, because this thing continues to blow my mind over and over and over again. I've been able to do mobile rendering on the Quest. That's where you start dealing with like reflections costing a little bit more because you get higher quality reflections. You still get all of the benefits that come with, the lower rendering pass, but you get a little bit higher shadow quality from dynamic shadows and real-time effects. Now, if you're doing a baked scene, like just stick with compatibility. You could pretty much get everything out of this rendering pipeline that you want in compatibility mode. I mean, even in compatibility, we're doing like dynamic clouds with a Perlin noise up here on top of this panorama sky, and it's running at full frames. And we're even getting, wow, I'm moving around really fast. And we're even getting some ambient light effects happening inside of buildings and some fog without any problem. So interior scenes look really good because you're able to use omnidirectional lights and interior based lighting versus like sun directional lights. You get to use point lights. So spotlights work and look really well. You have a ton of adjustments on like the mobile pipeline to adjust how lights behave. So that's something else that I probably can't speak on enough. That there's like a blur. There's opacity value. So if you want your shadows to be darker or lighter, obviously it's not going to update in the scene because this is baked out. But let me control Z that value real quick. But speaking of bakes, that's another thing. I don't know if you've been baking lights in Unreal, but if you're in GPU light mass, which presents itself with another slew of issues when you're trying to work within a forward rendering pass, but you're trying to use GPU bakes. You're almost in two converging technologies that don't really want to work very well together, or at least it feels that way currently in UE5. But in Godot, you just slam this lightmap GI node in here. You make sure that you've gone to your meshes and you've unwrapped for light maps. And then you hit this thing, and I want to say this thing takes about 13 seconds to bake out lights. I mean, it is almost nothing. Yeah, it's already re-importing the light. So yeah, it's about 13 seconds when it's all said and done. And this is true, even for fairly complicated scenes. I mean, CPU light mass is pretty quick in Unreal. It's not bad if you got a monster machine, 32 core AMD Threadripper or something. But the more complex your scene gets, even in a room like this with a fair amount of assets inside of it, especially if you're going to do something like 10 bounces, you're going to start paying a little bit. So Godot has GPU by default for light mass, and then it kicks a CPU in to like take up the slack if you don't have GPU, like a GPU capable to do it in these bakes. Yeah, I don't really know where else to go from here. Most of the shaders, like, here's another thing about having an engine that is GL based, is that, in Unreal, if you're using the shaders, using materials, you're usually using the material node. But if you've come from older engines, you're used to writing shaders, especially if you're in a 2D world. Like, you're used to writing shaders that manipulate your screen space, or manipulate some kind of overlay or compositor. You're just, even if you've used like Minecraft or like shader add-ons for other games, and kind of dug into that a little bit, you're going to be at least a little bit familiar with this kind of stuff. So, let me see. I don't think I've moved all the shaders. I can probably show you this sky shader. So, like, essentially, if you know how to write in GLSL, you can pretty much make Godot do whatever you want to do without having to like dive into like the RHI at the engine source level and making changes, because like the way that Godot works for the most part is it's like, define the shader type. Is it sky? Is it spatial? Is it, vertex? Is it pixel? Like, what is the pass you want to use if it offers that support? So like, do you want to render it at a quarter res and upscale? Do you want to render it at half res? And then you apply it to whatever you want to put it on. So this is like a spatial shader that I put on the clouds to give you like the Perlin noise. It's not very complicated. It's just put on top of the world environment for that stationary scene. Let's go open that guy back up so we can talk about it. So here, you'll see that I have a scene here. So this is my default scene. And it's cool because these are like prefabs. You can build them out and drag them into the world and then make them local and make edits to them. So they're like a class in and of themselves. And you'll see that all this is a mesh instance, a sphere mesh instance with a shader applied to it. That's it. And it kind of gives that low-level cloud effect inside of this environment. And it runs really well on a mobile GPU. I could probably get this thing down even cheaper than this without using the Perlin noise reference that we're using on the shader. By just, and it's just 16 by 16. I mean, super small. But I mean, I guess I could like put the noise texture, like generate it inside the shader, and it could be even cheaper than like this little lookup for this fast noise light. But this was provided, and it's still pretty cheap. And I mean, that's essentially like how the sky shader works. The sky shader is a little bit more complicated. I say a little bit. It's pretty, it's handling a lot of stuff. It has, sunset, night, stars, cloud coverage, cloud movement speed, texture overrides for the sun and and the moon. But again, still, it's a raw shader, and it's only using a quarter res pass to render, and it's extremely performant for what it's doing on mobile hardware. So I don't need to say that. Yeah, I figured now is a really good time to just kind of like break things down and talk about this from a perspective of an a developer or an engineer that's been, heavily involved in the Unreal camp, and I still love Unreal Engine. I have two projects, on the Steam Deck. I have, probably something that's classified as super high fidelity, or like getting approaching really high fidelity, because it uses Lumen. Both of my Steam Deck projects use Lumen, but my PC one for sure. But I'm actually debating whether or not, for me, it's all about using the tool for the job. So like, you know, either I can go outside and manually pick up sticks, or I can use a wheelbarrow, right? Like, sometimes using a tool can kind of go against the grain. Like if somebody was like, hey, write me an application that can run in HTML5 and presents with pretty decent visuals, I wouldn't go to Unreal. Like I would have to go all the way back to 422 just to be able to export to HTML, or I would have to go pull a custom branch. I think there's a third party that like actually went and did that and started working on it. But that's even a bit spotty. But yeah, there's a lot of like considerations that you would have to take into account about the lift or the burden that you would kind of put on yourself to start with a tool and go, well, I got to work on the tool and get it to a place where it can actually do what I need it to do before I can even work on the project that I need to complete. So in that regard, a lot of people's 2D choices and web development choice, like I don't want to say web development, the WASM choices, or being able to package out to WebGPU or WebGL, is going to be Unity and Godot. It's just the way it is. And I guess the thing that I'm stating is that like I'm starting to feel, with Epic's push towards like virtual production and high fidelity rendering and next gen consoles, deprecation of SM5 and DX11, and unification of the forward rendering pipeline towards higher end Metal devices and higher end Android devices, I'm starting to feel like maybe Godot is a better tool to achieve the performance and the visual quality that you would like to achieve. And it's not to say that Unreal isn't high quality. It is. It's just that the fact that it is so high quality and the way that it does things isn't really friendly to that mobile architecture anymore. That's not to say they're just ahead of their time. And I think Godot and Unity still have approaches. Vulkan subpasses, for instance, over in the Unity side, which I've read articles that'll be coming to, like it is in Godot already. They're using one of the most updated versions of Vulkan. So like you can essentially write a shader that will talk to a subpass or create a post-process like effect. You can actually do deferred lighting, by the way, in Godot, which is mind-blowing. So like you can create a subpass in Vulkan. You can tell Godot to render everything unlit, collect the depth information, and send the lighting occlusion data directly to the Vulkan subpass, which is extremely technical talk. But the point of the matter is that like they make getting from point A to point B within these target devices a lot easier than someone needing to go write USF and USH and modify huge chunks of the RHI in Unreal, and potentially even rewrite the way that they're dealing with light mass, light baking, to be able to target these platforms efficiently and have, pretty decent quality. A lot of people have chosen to stick with 427, and there's pain points there as well. But there's a ton of us out on the Wild Ox Studios Discord and Oculus Start, and I'm gonna shout out VRE once again. There's a ton of us out there that are still kind of supporting devs, that are hitting those headsets that are not wanting to kind of struggle with the current state that UE5 is in, with the amount of lift of modifications you have to do to make that either fall in line with what they want you to do or make that engine do more than what it can out of the box currently at 5.5. So anyway, remember to hit that like and subscribe button. If you have anything else that you would like me to cover or go over pertaining, the journey that I've been on with learning Godot, and kind of understanding its framework. There's so many things I could brag about with this engine that it does so well. One of the things is when I said VR, it being a viable solution. Unreal Engine does VR really well. I just did a DLSS4 video that covers, having global illumination, Nanite and Lumen running in deferred rendering with DLSS4. The trick there is that it's running in performance mode on a 2080 Ti, which is no slouch, just to hit full frames. And it's essentially downsampling the native resolution down to like a PlayStation 1 here roundabouts, and then upscaling it with AI and resharpening it. It's also a temporal solution with screen space, so it loses a little bit of its depth, and it has a little bit of weird artifacting in VR. If you were to look at Lumen, it's gonna seem a little strange because it's essentially a screen space effect. In flat games, doesn't matter. You can't really tell. Screen space effects are amazing in flat games, but in stereoscopic view, it looks, you can tell something wonky's going on. Same thing with a lot of all your metrics that are done in screen space. Godot uses a GI method called voxel GI. So if we go over here and we hit this and we go to voxel GI, it places voxels around the scene. It collects scene information, and then it bakes your dynamic GI into your map, which it's cheaper. It's not like a real-time GPU-based thing. It does take GPU and CPU to do this, but it's a like sign distance fields are kind of pre-built, they're pre-calculated. It's the same thing. It's a pre-calculated piece of data that accompanies an asset so that at runtime it's like Unreal's pre-computed visibility in a way, right? Pre-computed visibility uses a voxel-like system. Same thing with light probes. When you're baking out volumetric light in Unreal, they use light probes. Well, the light map GI in Godot uses the same thing. It just auto-generates them for you and only places them sparingly where it feels like it needs to. Voxel GI does the same thing for global illumination, and it runs in Forward Plus because there is no deferred renderer. You have GI in PC VR in world space, and you don't know what that feels like or looks like until you experience it yourself. And I'll leave it at that. So maybe in my next video, I'll go over like a little demo of what that look and feels like in real time for you guys. I've just been having a blast learning Godot and going over like what can this thing run on? And at this point, it's like, if I made a bet to someone that Godot couldn't run on an Abacus, I'd probably lose the bet. Like, this thing can run on a freaking TI-83 calculator is what it feels like. So it's really the little engine that could. It's impressive. It is 56 megs. It downloads in less than a minute on my internet speed. It opens up in less than a second, and you're pretty much on your way and started. I mean, within the blink of a snap of a finger. And by the way, if you haven't tried it out and you are a Quest owner, you can run Godot natively on the Quest. Just go look it up, download it. You can get started developing in Godot while you're in the VR headset, which is really crazy when you think about it. So it's been real, guys. Until next time, remember to hit that like and subscribe button. Go check out the Wild Ox Studios Discord if you're interested in learning how to develop in VR. Whether or not you're in Unreal or whether or not you're in Godot, there's a ton of people in our Discord that are in this space, that are willing to help out and that are extremely helpful. Until next time, guys, happy developing and toodles.